All right, we're going to do a brief review for our midterm, which is going to be this Wednesday. So in ChemDraw, you should be very comfortable drawing structures. We've done a lot of this during the lab, so hopefully that's not a problem for anybody. Remember, you don't have to keep on redrawing the structure from scratch. You could do the copy and paste, which makes things a lot easier. Then you only have to put in the new information in the second structure. You should be comfortable with the templates and the rings. Look through them, make sure you can make any ring size and use the templates effectively. And you should also learn how to justify your text in a structure. If you go under text, it'll say justify left, justify right, justify center. You want to justify it to where the bond is connected to the atom that's actually attached to it. So the melting point lab, the concept of the melting point is we're transitioning from the solid phase into the liquid phase by melting the material. Particle size is important. We want smaller particles so we get good heat transfer within it. If we have really large particles, the heat doesn't transfer and we get a broad range for a melting point. The rate of heating is also very important. If we heat too fast, we may actually achieve the temperature in our sample and see it melt before the thermometer actually gets to that temperature. So nice slow heating is what you need to do. The range of the melting point and the purity. Sometimes when we have an impure sample, we'll get a wider range for the melting point. When we have a mixture or an impurity, we're almost certain to get a lower melting point than expected. The concept of mixed melting points, if I mix two components together, I'm going to get a melting point for the material that's less than the melting point of either of the two components. And we can use this to determine purity of the sample as well. If we have a known melting point of a material, I could match it to what we achieve in the lab. Okay, the Recrystallization Lab. This is the one where we also did a filtration. So we heat up our material in a solvent, filter out materials that don't dissolve in that solvent. So now we should have a solution of the material that we want to crystallize. And then we can add an anti-solvent to that to allow the crystallization to happen. So the solvent is something that the material is soluble in, usually at a higher temperature. And the anti-solvent is something that it is insoluble in and allows crystallization to happen. And that's pretty much how solubility is related to the recrystallization itself. The Caffeine Extraction Lab. So we made tea and then we extracted the caffeine from the tea. So the solubility, the caffeine was more soluble in methylene chloride than it is in the water, and we extract it out of the water mixture with the tea. It's the first time we used a separatory funnel, and there's a picture of a separatory funnel here in the video if you didn't remember it. You should understand all the safety issues of using a separatory funnel. Remember, we have to keep on venting the gases that can build up inside that so the separatory funnel doesn't shatter. We want to make sure that our top is on securely. We want to make sure we're not pointing the tip of the separatory funnel at anybody when we're venting, because liquid could shoot out. Why do we do multiple extractions instead of one big extraction? It has to do with the partition of the material. We'll get some to dissolve in the solvent, and some is going to dissolve in the other solvent, which in this case was water. And we have that partition between the two. The more extractions we do, we're kind of forcing that extraction, kind of like an equilibrium, to go into the solvent that we're taking. As long as we're replacing it with new solvent, we can get more material to dissolve in it. So multiple extractions always works better than one larger extraction. And then we use a drying agent after we do the extraction. We dry it so when we concentrate it, we don't have water in our sample. And in our case, we use sodium sulfate Magnesium sulfate is also another good drying agent, and these stay solid in organic solvents, but they absorb the water from it, and then we can filter them away to get our dried solution, which we can then crystallize. All right, thin layer chromatography. You should understand how intermolecular forces are related to thin layer chromatography. There's an attraction between the silica, and the mobile phase uh, takes our material up the plate. The more polar the material is, the less it's going to travel. It'll adhere more to the plate. The less polar it is, the higher to the top of the plate that it's going to be. Right? And we can adjust the polarity of the solvents. The more polar the solvent, the faster the polar materials are going to move up, as well as the nonpolar materials. So this concept of RF related to polarity. So if I'm looking at two spots, the higher spot is less polar, the lower spot is more polar. And you should know how to calculate the RF. That's the distance traveled from the origin, which is the line that you draw on the bottom, to the solvent front line, the top of the plate, how far it could have traveled. And that's always going to be represented as a decimal. Okay, I covered which is more polar and which is less polar based on the RF. And we can use this to determine if a reaction is complete. If I know where the starting material spots, I know where the product spots, I could monitor a reaction and see the starting material converted to product. It could also be used to determine purity of material. If my material is pure, I should see one spot by TLC. If I see more than one spot, I know that it's not pure material. Okay. The column chromatography. So this is really just an inverted TLC plate. The TLC is used to mainly analyze the reaction. Column chromatography uses the same exact principles, but to isolate materials. So we're trying to collect the fractions. So it's a larger TLC plate per se to try to get our material out. The material that'll come off the column first is the least polar material. The more polar materials are going to stick to the column and require a longer time to come off. The distillation lab, you should understand the vapor pressure and boiling point relationship. So the higher the vapor pressure is, the more the material wants to go into the vapor phase, the lower the boiling point is going to be. You should understand the parts of the distillation apparatus. We had our flask, the Claisen head, which had the thermometer in it, and then the condenser, which allows our vapor to cool down. And then we divert it into a flask that we can collect our material in. The condenser works by having cold water go in at the bottom and out at the top. It fills up. It's a jacketed condenser, which allows cooling so we can get our material out of the vapor phase into the liquid phase. You should know how to read a boiling point composition curve, and I'll go over that in a second. And you should understand the temperature versus volume graph that you had to make for the lab. So let's start with the boiling point, the vapor pressure, the composition curve. All right, so this first thing we have here at this point at concentration 1, this would be the boiling point. So this temperature would be the boiling point of the liquid at this point. So the composition is more enhanced in component B at concentration 1 in the liquid phase. But if we look at what's going on in the vapor phase, work our way across, we can see that it is more enriched now in component A in the vapor phase. So what this means is that A is the more volatile compound, the one with the higher vapor pressure, and B is the one with the higher boiling point and lower vapor pressure. Okay. The temperature versus volume of distillate curve. This is what a normal curve should look like. I should be collecting a fraction at its boiling point. Sometimes there's a dip, and then there should be a sharp rise when I'm transitioning between the two components, and then there should be a nice straight line for the boiling point of the second component. We rarely see this happen. What you wind up looking at most of the time is an S kind of curve. So what actually happens is you'll look at it and we'll see something like this, and where it's just kind of rising up, and then maybe it'll level off at the boiling point of our material. And this is what yours probably looked like. It all depends on how slowly we do the heating and how good of a separation we have within our column. A fractionating column gives us a better line. We did not use a fractionating column. All right. So hopefully this helps. I also posted a list of videos on all the experiments that we've conducted that go through them. They're a lot longer for you to work your way through, but I think they're worth listening to, and those are posted in the announcement on Canvas. All right, everybody, good luck, and I'll see you on Wednesday.